Fluctuating stresses are time-dependent stresses. As shown here, the stress is varying like this. It is time-dependent. As time is changing, the value of stress is also changing. Here we can mark 2 points: maximum stress and minimum stress. So the stress will vary between these 2 points, maximum stress and minimum stress. Now we can define the stresses on the basis of these two parameters, maximum and minimum. There's two main parameters. That one is mean stress. This is given by maximum plus minimum by 2. Then the stress amplitude is given by maximum minus minimum divided by 2. So these are the two values which we'll be using in design. And another important fact is that we are not bothered what is happening between the cycle. If we see from this to this one cycle, stress is varying here, stress is again fluctuating here. But for designing, we are interested in maximum minimum value. So from now onward, we will represent the stress by simple sinusoidal wave, just to represent the maximum value and minimum value, and we are not bothered how it is varying if some change is also taking place within the cycle. So now there are few more parameters that need to be defined for further analysis. One is stress range. The stress range is designated by R, and it is maximum difference of maximum and minimum. Then we have stress ratio. It is given by it. The stress range is represented by sigma R rather, and stress ratio is represented by R, given by sigma minimum over sigma maximum and amplitude ratio. And amplitude ratio is represented by A, given by sigma A over sigma M. Again, sigma A is the stress amplitude, sigma A is known as stress amplitude, sigma M is known as mean stress, and ratio of stress amplitude to mean stress is amplitude ratio. Now this mean stress is static component, equivalent to static component. For this case, this may be mean stress. It's not always necessary that 0 point will be the mean stress. The mean stress may be above 0 or below 0, and mean stress will be time independent. The curve of mean stress may be like this. The curve of mean stress may be like this, depending on the values or value of minimum and maximum. It may be above 0 and below 0, but it will be constant. It is time independent, so that is why this is considered as equivalent to static load. Whereas sigma A is difference of sigma maximum minus sigma minimum and 2. Now these two are the component. Now we can assume that sigma A is the stress amplitude. This is superimposed on sigma M, will give us the fluctuating stress. So this is these are the few things, basic introduction of fluctuating stresses. Now if we see what is the harm of fluctuating stress and why it is so important to design differently for fluctuating stress as against static stresses, where we have design number of components using simple design equation that maximum stress should be less than equal to design stress. This is our basic design equation, that maximum stress is equal to less than equal to design stress, where maximum stress is the stress at a point on any component which is subjected to any kind of load. If it is uniaxial load, we can find out maximum stress by using sigma is equal to F by A. If it is axial load, we can find out maximum stress if it is bending, that is M maximum, where bending moment is maximum, over I about neutral axis into Y maximum. This will give us sigma maximum and sigma maximum here. Likewise, if it is shear stress, we can find out tau maximum, that is equal to MT maximum divided by J into, that is about axis which is passing through the two neutral axes x and y, then it is R maximum. So this is how we can find out value of sigma maximum. This axial load, bending load, and tau maximum is twisting moment, or sometime tau maximum can also be obtained by simple F by A if it is only in plane shear stress. So we have used this maximum stress less than equal to design stress for static load, but in fluctuating stresses the design equations are no longer this. This is for uniaxial case of load. If we have biaxial state of stress, in that case this maximum stress or the design equation will take form of any theory of failure. So in biaxial state of stress, we make use of theories of failure, theories of rather static failure, and we make use of those some of the theory of failure, one or two theory of failure, or sometime one theory of failure to predict the failure or to design the component. What happens if we apply fluctuating stresses on any component is that that can be understood with a simple example. If we want to break a simple 4 mm 5 mm steel wire, what we do is first punch it to make a notch, and then we can use our hand to apply bending stresses. We bend it in one way, then reverse the bending, and we keep on changing the stresses, and finally you get a broken wire, which otherwise not possible through only axial load. So that is why it suggests that it is not SYT or SUT, that is ultimate strength or yield strength, which are responsible for failure. In case of fluctuating stresses, it is something else, which is defining the failure, and that we obtained. What that parameter is, we obtained through one experiment known as fatigue test. We conduct that test on standard fatigue machine and plot the curve between stress and number of cycles. We conduct the experiment by loading one specimen, standard specimen, and then rotating that particular specimen under load so that it is under variable or fluctuating stress for under bending load. So in that case, if we plot this, we get this type of curve. If it is for steel, and here we take log of n, and here it is simple linear graph is there. This value is 0.9 times SUT, and this value is approximately 10 to the power 3. If we log 10 to the power 3, it is 3. And after some time, after this much number of cycle, this curve become parallel to x-axis, which is RPM here log n, and this value is 6. That 10 to the after 10 to the power 6 cycle for steel approximately, this curve become parallel to this. So it means we have some value which is equivalent to this if the stress induced in that component is below this value, then this component will not fail for infinite number of cycle, for any number of cycle. So if we have this point that we have marked here, and we have obtained this point experimentally, this point will represent that this point is loaded for some with some load such that the stress induced here is SF, and if we have loaded that which is which induces stress of f dash, then this value is log of n. So this much number of cycle this particular component will complete before the failure. So it means this and we have now two salient points. These points can be infinite on this curve. For each point we have two values. One is the stress and another is number of cycle, and we have specific name for these points. This particular point for which that component can be loaded for infinite number of cycle is known as theoretical stress concentration factor. This SF is sorry, this SF is known as fatigue strength. So we have SE dash, this is endurance limit. We have SF, that is endurance strength. So there are two names for each. SF is endurance or fatigue strength, and SE dash is endurance or fatigue limit. Here it is important to understand that fatigue limit means we can apply that much amount of stress for infinite number of cycles. The component will not fail irrespective of the number of cycles. SF, fatigue strength or endurance strength, is associated with some with finite number of cycles, and it means that SF is the amount of stress that a component can be subjected to for safely for NF number of cycles. And another important aspect here is that this any design between this to this limit is called finite life design, and any design below this limit is infinite life design. So we have two design aspects here for the fatigue stresses. One is finite life design and another is infinite life design. So we will be discussing both these aspects for finite life design and infinite life design. And this fatigue before this 10 to the power 3 cycle or 10 to the 4 cycle is known as low cycle fatigue, and then it is high cycle fatigue. So next lecture or this next video will be discussing how to design a component, or first we will discuss how to modify this SE dash, because we have used this as theoretical. This is basically theoretical endurance limit, though we have obtained it experimentally, but still it is called theoretical endurance limit, and we have to modify this endurance limit to get the final value of endurance limit with the help of some factors that we will discuss in next lecture. Thank you.